Hello, everyone. Hope you're having a pleasant Monday without lecture at 9 a.m. I will see you Wednesday at our usual time. So today I was looking back at the lecture from Friday. I was going to post it and realized that for those of you who are there will realize I said something dumb without thinking, sort of made a rookie mistake, as you will. We're talking about ferrite growth, and I said something off the cuff related to the diffusional aspects of growth without thinking about the driving force for growth, and in a sense made a mistake that a couple of you made on the exam. So I decided not to post that because I didn't want to cause confusion. So what I'm going to do now is go through the ferrite stuff. Through the perlite growth stuff is one solid lecture. And when I get to the specific part on growth, I'll point out where I made my error in talking off the cuff instead of following what I actually had written down in the notes. Okay, so just a refresher that perlite is composed of layers of ferrite and cementite. It is not a single thermodynamic phase. And I stole the analogy that Sir Harry Badisha made about comparing the structure of perlite to that of a cabbage. So we've got this interconnected, interwoven lamellar structure that grows out. And even though it's convoluted, it's generally largely spherical and equiaxed shape. You don't normally see cabbages that are elongated, just as we see colonies of perlite that tend to be equiaxed as well. In this image, the red from the cabbage would be the cementite, and the white would be the ferrite. All right. So in this case here, we see this is a hypereutectoid steel. We have proeutectoid cementite growing on the prior austenite grain boundaries, with the perlite colonies essentially taking up the entire prior austenite grain. Okay. So the growth of perlite, we spent a little bit of time on Friday discussing the structure, right? How the lamellae of the ferrite and the cementite are roughly parallel, right? And with a uniform wavelength. And we sort of speculated as to what could make that happen, right? And we'll get to the exact mechanisms for that in just a couple minutes. So for those of you who weren't there Friday, don't worry, you haven't missed much. We mentioned that there's two observed orientation relationships: this pitch-petch orientation relationship and the Bagriatsky orientation relationships, and that if the perlite nucleates on a clean austenite boundary, right, one that does not have any cementite on it, you get this pitch-petch orientation relationship, and that the orientation relationship is formed with respect here to this gamma 1 grain, right? So this would be a coherent boundary here between the austenite and the perlite that would follow the pitch-petch relationship, and we would grow into the gamma 2 grain And this, in general, will be a incoherent high energy or high misorientation boundary, right, that has significant mobility. So this would then be an immobile, relatively immobile interface. This interface would be able to grow. If we have proeutectoid cementite at the grain boundary, we have a situation that looks like this, right? So here's the grain boundary cementite layer. We then have the ferrite laths that grow off it, right? And again, this is an immobile boundary. This is mobile, and this tends to form the relationship of the cementite with the alpha forms this Bagriatsky relationship, right? And the cementite in that case is related to the grain, right? This cementite orientation is related to gamma 1. The ferrite part is not related to grain gamma 1 or the orientation of grain gamma 1 or grain gamma 2, right? Okay. Right. And this basically just says the same thing, that if it comes from a clean orientation relationship, you get a pitch-petch, and that the pitch-petch relation, it's not important to memorize it exactly, but just remember that know that it's close to Kurgyamov-Sachs. Like most things in steel, we have a lot of things that are close but not exact. Pitch-petch is close to Kurgyamov-Sachs. Right? Okay. So the nucleation of a pearlite colony occurs by something called sympathetic sideways nucleation between the ferrite and the cementite layers. And this is easiest to explain on this figure here. And so let's pretend we have this ferrite layer growing. And as it grows, it has to partition carbon, right? The ferrite is essentially at 0% carbon. The austenite, the austenite is nominally at this value here, but we have from the partitioning, we have this diffusion field, and we have a gradient in carbon concentration from the interface of the austenite from the austenite and the ferrite interface into the bulk austenite. And basically, this carbon concentration will get larger and larger until, right, if this is growing faster than the carbon can diffuse away, what that means is that eventually we'll build up a concentration high enough to nucleate a layer of nucleate a layer of cementite. The same thing happens here. If we have cementite and it's growing, it has to diffuse carbon into it. So near the interface is carbon poor relative to the bulk austenite composition, and eventually that carbon concentration gets low enough to nucleate a layer of ferrite. And that's what we refer to as sympathetic sideways nucleation. You can imagine if the temperature is constant, our diffusivity is constant, and our driving force for growth is constant. So that means we get essentially a regular wavelength. The spacing between the ferrite and austenite, or the spacing between cementite and cementite layers, is basically constant. But of course, we can have fluctuations, and we can have defects, right, that lead to branching and coalescence, just like in any other growth system. So we have a constant wavelength, but it's not 100% perfect. So now, if we think about diffusion, what temperature is going to do to this, right? So basically, at higher temperatures, we've got two things that are going to happen. The mobility of carbon is faster, right? So this can diffuse away. And at higher temperatures, our driving force for growth is less. So this is going to be growing slower. So we're going to have a slower moving interface and faster diffusion of the partitioned carbon away, which means that our distance between the cementite laths is going to increase with temperature, right? And so this is where I confused myself completely in lecture. So in lecture, I spit out the right answer, and then when I got to this slide, this is reciprocal temperature. So I confused myself and said the exact opposite, and then realized I made a contradiction and had to work it out. But in reality, I just don't know how to read a reciprocal graph, right? So we have a linear relationship between the reciprocal of the spacing and the degree of undercooling. So the reciprocal here, this is large spacing, this is small spacing, this is high temperature, this is low temperature. So at high temperatures, we have larger spacing, as our diffusion and driving force argument would say, and at lower temperatures, we have a finer spacing. Again, at higher temperatures, we have less driving force for growth, so our interface isn't moving as fast, and we're able to diffuse the carbon out. So we have a wider spacing. I'm not going to go through a formal derivation of this, but just the general trends. Oh, and also here, right, if we look at alloying elements, right, can have a fairly profound effect on the spacing. So if we just have carbon, we're here. If we add cobalt, right, we can really change our pearlite spacing, right, and the temperature that we need to grow it at with the addition of small amounts of alloying elements. Okay, so the growth of a pearlite colony is accomplished by the addition of lamellae, either by branching of the lamellae or through the extension outwards of the ends of the lamellae, right? So the addition of lamellae, right, if we nucleate, let me go back here, right? And we come to this figure, right? We can grow side to side, parallel with the grain boundary by adding new lamellae, right? We can branch, which makes it wider, or we can continue to grow this way. We can extend the lamellae, right? And basically, the pearlite colony has an equal rate of growth in directions parallel and perpendicular to the lamellae because we have these different growth mechanisms, right? We end up with a pearlite nodule that is basically spherical in shape, right? And when we section it, it usually looks like a circle. Okay. These pearlite colonies will continue to grow until they impinge upon adjacent colonies, right? And so during this time, before impingement, the rate of growth is basically constant, right? After impingement, the pearlite nodules can only grow into the remaining austenite between the pearlite colonies, the pearlite nodules, and this is the last stage of pearlite growth. Now, the rate of growth is also a function of temperature, right? And so at just below the eutectoid, we don't have a lot of driving force for growth. We don't have a lot of driving force for the phase transformation. So we have fairly sluggish growth rates. As we decrease the temperature, we increase our growth rate until then we hit a maximum where we start to decrease, right? And this is in the range where we start to become diffusion limited. And usually this is where other mechanisms such as bainite will take over. Okay. So the isothermal growth rate decreases with temperature, right? Or the growth rate at a constant temperature, the isothermal growth rate stays the same, right? It's a constant with temperature. The isothermal nucleation rate increases with the time at temperature. We get the sigmoidal. So the longer we hold, the number of new nuclei that we have starting increases, right? And so I want you guys to think about the physical origin of this, right? We'll talk about it, but I want you to ponder it for a little bit. And it has to do with heterogeneous nucleation at the grain boundaries, right? The pearlite colonies are always nucleated heterogeneously at the grain boundaries. So why would that give you a nucleation rate that changes with time, right, for a given constant temperature? Think about it for a little bit. We'll talk about it. Okay. As the reaction temperature is lowered, right? So here's our rate of growth. Remember, it takes that, we start out low growth rate, go to a maximum, and then decrease again, right? The rate of nucleation increases a much faster rate than the rate of growth, right? And that as we lower the temperature, our rate of nucleation becomes higher than our rate of growth. So if we're at a isothermal hold at a high temperature or a low cooling rate, basically growth is faster than nucleation, right? Growth is faster than nucleation. And so we get one large perlite colony, basically, that will consume an entire prior austenite grain if it's hypereutectoid. If it's hypoeutectoid and we don't have grain boundary cementite, one perlite colony can actually consume a number of austenite grains. The opposite is true if we have a lower temperature hold or a faster cooling rate. The austenite grain boundaries become outlined by a large number of perlite colonies, right? Nucleation is easy. And they'll grow slower, but they'll grow and impinge on each other. So we will have a number of perlite nodules that grow into a single austenite grain, right? And when this is happening, when we have nucleation that is faster than the growth, right? We need to think of these things in terms of grain boundary nucleation. And the analysis of the transformation is more difficult. It doesn't follow JMAC theory, right? And our overall transformation rate is going to depend on the prior austenite grain sizes. And the transformation rate decreases with increasing the austenite grain size. So the amount of time it's going to take our entire structure to be transformed becomes a function of the austenite grain size, right? So the strength of the perlite is proportional to the degree of undercooling, right? And this is completely related to the interlamellar spacing, right? So our strength is going to be dictated by basically Hall-Petch effects. The closer the lamellar layer, the stronger our perlite is going to be, right? And right, we can see right? That the more that we have a a fairly linear effect with the degree of undercooling. The work hardening is also going to increase with the perlite content. Perlite work hardens faster than ferrite, large ferrite grains. And again, this is because of the interface and the dislocation reactions of the interface. Okay, but perlite has an adverse effect on toughness, right? Crack nucleates along the ferrite cementite interfaces, right? The interesting thing is that we have a wide transition temperature, right? So basically the crack crosses the lamellae, right? Every time the crack propagates across another lamellae, we're going to absorb energy, right? At each crack, right? So we're going to have many cracks that nucleate at the interface and a very high work hardening rate, which limits our plastic deformation zone around the cracks. So we have a low energy absorption situation, right? And we can see that the effect of this here. Okay, so that's the gist of ferrite and ferrite perlite. It's pretty straightforward, just conceptually understanding sympathetic sideways nucleation, and the growth rates, trends that and property trends that we had talked about. So I'd like to talk just a little bit about ferrite perlite steels, because this is a huge fraction of the total tonnage of steels that are used in industries. Manganese is added to tie up sulfur, which leads to a whole host of unwanted properties. But it also gives us is a very potent solid solution strengthener, right? And they're also manganese, aluminum, and silicon are deoxidizers, right? They form intermetallics with the oxide, takes it out, and aluminum is also a grain refinement and strengthening. And there's two important heat treatments for these plain carbon perlitic steels: normalizing heat treatment and an annealing heat treatment. So normalizing heat treatment is 100 to 150 degrees C over AC3, right? So we're in the austenite range, and then we cool, typically air cooling to room temperature. So we go down through the transit, and the goal of this is to refine the grains and develop a relatively fine perlitic structure, right? And we also want to optimize our carbide size and distributions for subsequent processing, right? And so the normalizing heat treatments are commonly used during production of plate. So after hot rolling, or during hot rolling, there's a slow cooling that occurs from rolling temperature. And this gives us very large grain sizes and very coarse carbides. And this structure is very difficult to heat treat, right? So we normalize the steel to make normal again, so that we can go on with subsequent processing, right? And we want to keep it fairly low above the transformation temperature, because we don't want the austenite grains to grow too much, but we want to allow the large carbides that have grown, to dissolve, right? And then we air cool to produce a fine grain microstructure with a good fine carbide distribution, right? In actual processing, normalization is done at a continuous furnace, right? So we take our steel, our strip steel, and it's rapidly heated to the normalization temperature, and then air cools it, exits the furnace. So it's just rolled through basically a hot zone in the furnace, and depending on the product, sometimes forced air cooling might be used. The other processing heat treatment is a full annealing heat treatment, and this is we want to take it to relatively high temperatures. We want to dissolve all the carbides, and then we want to cool below the equilibrium temperature, right? Slowly cool it just below, excuse me, the equilibrium temperature, and this gives us a complete transformation to ferrite and coarse pearlite, right? And this gives us a very soft, easy to machine steel, right? But it has a low strength. So a full anneal is what I was just talking about. We held at a high temperature and then slowly cool it to below the equilibrium transformation temperature, and then we slowly cool through the transformation range so that we have only ferrite and pearlite. But this is can be a very time-consuming process. So instead, what's often done is what's called isothermal annealing. So we take it into the austenitic region, we dissolve all the carbides, then we rapidly cool it below the A3 temperature, right? And then allow it to transform at a constant temperature. And what we're trying to do is control the temperature relative to the nose of our CCT curve. This is the coarseness, describing the coarseness of the pearlite. So we end up with a nice coarse pearlitic structure. And this process can be much more time efficient than full annealing, right? So if this is the temperature, here's the conventional annealing, right? And we have to cool slowly to make sure that we're in this coarse pearlite region. With the isothermal anneal, we rapidly cool. We make sure that we're still out front of our CCT curve. Then we hold that temperature and allow the pearlite to nucleate and grow. And this gives a more time-efficient process than full annealing. We can use it for batch annealing. Basically, you can make a whole bunch and put it into a large furnace and anneal everything at once. And it's more homogeneous because our complete section sees the same temperature, rather than when we're continuously cooling, the outer portion of our steel is going to cool faster than the inner portion. So as I mentioned before, most of our commercial steels are going to contain alloying elements. Plain carbon steels contain anywhere between 0.5% and 1% manganese, and a little less than 0.5% of carbon. And these are for a lot of times for production economy, right? And we want strengthening and to suck up oxygen. Low alloy steels, right, contain additional alloying elements such as cobalt, chromium, molybdenum, nickel, right, in concentrations that can go up to several percent, right? And in some low alloy steels, we can even increase the manganese concentration, so we could go up to as high as 5% manganese, right? All of these steels, basically, when they're in use, we're using them as pearlitic steels. So we need to understand how these alloying elements are going to influence the transformation and the transformation rates. So our alloying elements can alter our eutectoid temperature. Nickel and manganese tend to make austenite more stable, right? They act, in other words, to decrease the eutectoid temperatures. Silicon, chromium, and molybdenum increase the eutectoid temperature. They make austenite less stable. We can also change the growth rate or the transformation rate of the pearlite reaction. Right. So cobalt is unusual because it will retard the pearlite transformation. All of our other common alloying elements. Oh, shoot. I said this backwards. All others act to retard the transformation. Cobalt is the only one that accelerates the transformation. I'm sorry about that. Silicon, chromium, and molybdenum raise the eutectoid temperature. The pearlite transformation tends to occur earlier at high temperatures in steels with these elements more than it does in plain carbon steels. Remember, the plain carbon steels will also have just a little bit of manganese in them. At lower temperatures, though, the transformation rates in alloy steels tend to be slower than those in pure iron steels. And basically, here's just sort of the a trend in lamellar spacing and how the different alloying elements. So here's plain carbon steel here, and so what we see is for a given temperature, chromium makes the lath spacing finer. Remember, this is reciprocal of the spacing, and manganese tends to make it larger. Right. So the other thing we have to worry about is, because we're slow cooling this, our alloying elements may also be partitioned between the ferrite and cementite and the pearlite as a result of the pearlitic transformation. So the alloying element that was in solution in the gamma phase in our austenite doesn't necessarily remain only in our ferrite part of our pearlite after the transformation. Part of it can be incorporated into the cementite, right? So then our cementite in the pearlite is not just Fe3C, but it can have iron atoms that are replaced by atoms of the varying alloying elements. So we have to, there's some significant factors which are important for understanding how this partitioning or when this partitioning is going to occur. So the partitioning of the alloying elements between the ferrite and the cementite, right? This is all thermodynamically driven, right? And so if we're doing things slowly and we're approximating equilibrium conditions, right, partitioning is going to be favored by a low degree of undercooling or when our supersaturation is small, right? And alloying elements that have a strong affinity for carbon are generally known as carbide formers. They're going to have a strong tendency to partition to the cementite of the pearlite, manganese, chromium, molybdenum. Silicon, nitrogen, and cobalt are going to concentrate in the ferrite partition, right? And if the supersaturation of carbon is high, right, like in a large degree of undercooling or correspondingly fast rate of transformation, we can suppress this partitioning, right? So hypereutectoid steels are going to tend to partition much less. The alloying elements are going to partition much less than hypoeutectoid steels. The temperature interval where the solute partitioning occurs, the pearlite growth rate is controlled by the diffusion of the alloying elements along the grain boundaries, right? It's grain, we're mostly occurring by grain boundary diffusion, not by bulk diffusion. Unless we're at lower temperatures, partitioning doesn't occur, then our growth rate is going to be controlled by the volume diffusion of the carbon atoms, right? So if we're at lower temperatures or high supersaturation of carbons, carbon controls the growth rate. If we're at high temperatures, where we have less of a driving force for transformation, our rate is going to be governed by how fast our solute atoms can partition. But in general, there's going to be some temperature above which partitioning does occur and below which it's not going to occur, right? And this is a no partition transition temperature. Excuse me. And it's a characteristic of the composition of the alloy, and it's going to decrease for any given alloying element, right? And increase with its concentration. So the more supersaturated our alloying elements become, the greater this partitioning happens. All right. So here we see the three basic things that we talked about. Here's the pearlite growth rate as a function of temperature, our pearlite lamellar thickness, and how much partition. This is the partitioning parameter here. So for manganese, our partitioning parameter is quite large at high temperatures, right? So that means here we're going to partition into the cementite at high temperatures, but at here, when the partitioning parameter is 1, this means that we don't have any appreciable partitioning. So here our no partition temperature is going to be about 670 C, or 943 K is roughly our temperature, right? And the greatest partitioning happens just right below the eutectoid temperature, right? So the properties of plain carbon steels, plain carbon ferrite pearlite steels, right, are going to depend strongly on our carbon concentration and our manganese alloying concentration. And we can do some statistical analysis to separate out these two effects. And so if we look at the effect of the carbon content, right, we've got this solid solution by manganese, which is basically a flat line because we're holding our manganese content constant. We have grain size, and then we have a strength effect due to the formation of pearlite, right? Because remember, pearlite is much stronger than plain ferrite. Now, if we hold carbon content constant and we adjust our manganese, we see that we get an increase in strength from the solid solution strengthening of manganese, right? We get a grain size effect that's fairly constant, and then we get a more modest strengthening effect from the pearlite. And one of the questions I'm going to ask to think about is, it's pretty obvious where this big effect for the the degree of strengthening due to perlite as we increase the carbon content, but I want you to think about why we get an additional increase in strength, a modest increase in strength from the perlite content by increasing the manganese content. So go back and look at the trends and see what you can make of that. Right? Right. Oh, dang it! I put the answer there. I forgot I did that. Manganese, right? We changed their eutectoid temperature, right? So our eutectoid happens at lower carbon content, right? Which means we get increased perlite formation with the addition of manganese. Okay, and we can, if we add very modest, very small amounts, less than 0.1 weight percent of aluminum, vanadium, titanium, niobium, we can get refinement of grain sizes. So aluminum, for example, forms fine aluminum nitride particles, right, which form at the austenite grain boundaries, pinning the austenite grain boundaries and restrict grain growth, right? And so we can get austenite or ferrite grain sizes of 5 to 6 microns if we have a very modest addition of 0.03 weight percent aluminum nitride, right? And when we have alloys like this, we can generally use them in the hot finish condition, right? So we don't need to do any further cold working or heat treatment, so we can use them, produce them very cheaply, and these tend to be steels with less than 0.25 weight percent carbon. And so we don't lose too much ductility. And these types of plain carbon steels are most often used in our structural applications: I-beams, bridges, buildings, ships, right? Are large large classes of structural steels. We can then cold work them or warm work them by rolling, which gives us a better finish and an increased strength. And for really high quality sheet, we do subcritical annealing, so we're below our equilibrium temperature. So we're not going to re-austenitize, but we're going to allow for recrystallization in the ferrite. All right, and so we can get yield strengths of 240 MPa, elongations of about 30%. Right, and that wraps up our perlite. On Wednesday, we will start to talk about bainite. And I look forward to seeing everyone again.